investigations. It's on magneto-mineralogy, as you can see here. Also, all people had been in the field, and we have seen the group before on the presentation. I put here two of my colleagues or co-workers, so because they have produced now the data. It's Johanna Berghahn. She's my PhD student and has supervised the data to produce the data. And Marek Hübner, he is one of our student worker, and he is going to do later this year his bachelor's thesis on these samples. So that's just why I put them here also as co-authors for this presentation. So I came to this expedition due to a GFG project, and I'm coming from KIT in Karlsruhe, Germany. And my aim was to look at the rock magnetic properties, for the different volcanic rock units, because I have a similar project in Central Europe, investigating alkaline volcanics and looking for the magnetic mineralogy there. And I thought it's a good idea to compare those with the ones I can sample here in Spitsbergen. So these are some questions: rock magnetic properties, how is a magnetic mineralogy composed? Can we differentiate between crystallization and cooling? Crystallization and cooling mechanism. So we can learn something from the titanomagnetite on cation order or cation vacancies. Are the titanomagnetite altered? It tells us something on the history of these volcanic rocks. And can we differentiate different volcanic eruptive sequences? So before I come to the first results I want to show you, I first want to give you a very quick introduction. What is magnetic mineralogy? And for that, I will show you a few basics on the titanomagnetite solid solution series and how to determine magnetic minerals and their characteristic transition temperatures, and what can we learn from it. And then I will show you the first results from the Woodfjorden area in Spitsbergen. So first, let's start with the structure and phase relations in the titanomagnetite solid solution series. It's very basic what we can see here. It's a structure of magnetite. So the titanomagnetites are actually inverse spinel with tetrahedral A and octahedral B sides, where your iron 3+ and iron 3+ and iron 2+ are situated. And for the titanomagnetites, you see it over here. You have the solid solution exchange where you have two iron 3+ that are substituted by iron 2+ and titanium 4+. And you have as end members of this solid solution series the ulvospinel as a titanium-rich end member and the magnetite on the other side. And you have the magnetic properties of the solid solution series are also changing with composition. What you also see here that you have a miscibility gap below about 450 degrees, and in volcanic rocks, when you quench your magma very quickly, you retrieve compositions from that. You retrieve this composition without exsolution. Only if you have some special things, subaerial emplacement, degassing, and things, you might have some exsolution features, and you do not have this original titanomagnetite composition. So, as I told you, there is a relationship between composition of these titanomagnetites. So here you have the ulvospinel with a Néel temperature at -153 degrees. And here you have magnetite with a Curie temperature of 580 degrees. And you see there is a linear relationship actually between composition and Curie temperatures. So that might be interesting. And because then, so what I'm doing, I'm using the temperature dependence of magnetic susceptibility to determine these Curie temperatures. And from these Curie temperatures, so here we have, this is an example now from HSDP drilling, Hawaiian Scientific Drilling Project. We had been in Hawaii before in your talks where, so this is from drill course of the HSDP, ICDP drilling. And what we can see here is this is susceptibility versus temperature. And we see here the Curie temperature. It's this temperature here around, and we can determine a composition for this titanomagnetite. And this is a titanomagnetite. You see here, it's primary crystallized, it's homogeneous. This is a half micrometer, 500 nanometer size here. But you also can see, especially in lava flows, this in subaerial basalts, you can see this exsolution, high temperature exsolution features. As you see here, these titanomagnetites are not homogeneous, and you also see it in their magnetic properties, because now you have ilmenite plus titanomagnetite with a much lower titanium composition, and therefore you get much higher Curie temperatures. So I think these are the really two things you can see in volcanic rocks. Yeah, if you have fast quenching and if you have oxy-exsolution, you will see this. But you can also see something other in volcanic rocks. And actually, this observation, for probably people have seen it, but they haven't documented it very well. And as you can see, there's one work now from Jackson and Bose in 2014, where they showed that Curie temperatures might be very, very different if you compare now cooling and heating legs. So let's just go back. What's shown on the next slide is the Curie temperature from here and from here. Yeah, so here you see it's quite comparable, but there is even a small discrepancy. But now here you see this is an example from pyroclastic rocks of Mount St. Helens. You also have these homogeneous titanomagnetites. You would expect only one Curie temperature, homogeneous, high titanium concentration. But what you see here now is that your Curie temperature from the heating leg is much higher than the Curie temperature from your cooling leg. Yeah, so, and therefore Curie temperature, they said that Curie temperatures might be an inaccurate proxy for composition in natural titanomagnetite, but these cation reordering processes that they assume are documented here may provide you a tool for constraining thermal histories, yeah, of the titanomagnetite bearing rocks. So we have also found something similar in titanomagnetite from Mythina. So we have published it together with Horst and a master student, Philip Lied, here. And what we have seen here, so this is a quite similar rock as we will see that we have seen then also in Spitsbergen. We have chromium spinel, and we have titanomagnetite rims, and we have these titanomagnetites here in the matrix of the volcanic rocks. And we have determined a composition of this titanomagnetite by an electron microprobe. And we have calculated now Curie temperature from this composition. So you can do it the one way or the other way around. Yeah? You can take a composition and calculate your Curie temperature. And the Curie temperature that we have calculated is 208. But then we have also these temperature-dependent magnetic susceptibilities, and there you see that they are looking very irreversible, the heating and the cooling legs. But what is very obvious, that the cooling Curie temperature is always the same here, and this correlates with what we have calculated. So the cooling Curie temperature is what you see in the composition, and this gives you the titanomagnetite. And from these irreversibility behavior that you can, I don't want to go into detail, you can learn something. And what this I haven't shown you before because this strong irreversibility, it has something to do with magneticization. So it has something to do with the oxidation of your titanomagnetite. And just one look here, it's a sample from here, this type 3 with looks like this. We have it here. This is a backscattered electron image. You see some model textures in here. And this is a temperature dependence of magnetic susceptibility. It's a heating curve. And then we have the cooling curve. And once done in an argon atmosphere and once done in air. And you see a clear difference. And we have also done these SEM images. So this is before, and this is after heating in argon. And you see the titanomagnetite is very homogeneous, related to this Curie temperature, to this composition. And in this case, when we are heating it in air, you see a decomposition. And this is actually the high temperature oxy-X solution that I have shown you before. And this is what we see here. Susceptibility goes down because you have some ilmenite forming, but your composition of the titanomagnetite doesn't change anymore back. Okay. What this magnetization do is it increases your originally homogeneous titanomagnetite Curie temperature to higher temperatures. That's actually what we see in this irreversibility. Now let's have a look on the magnetic properties from the Spitsbergen sample. So first, what we have done there, we have measured magnetic susceptibility. And magnetic susceptibility, it sees not only the titanomagnetite, but it sees a whole range of minerals. Yeah, so we can have paramagnetic minerals, we have the diamagnetic minerals, they don't contribute much then. But as you can see here, if you have only a little bit of magnetite or titanomagnetite, only a little, we have a much higher magnetic susceptibility as only we would have paramagnetic minerals. And we can measure this magnetic susceptibility with a copper bridge that is shown here. It's from our lab. It's we have now a new one. It's a Carl Y5 copper bridge from Agico, and we have done our lab measurements with this instrument. But in the field, we have also done magnetic susceptibility measurements using a handheld copper meter. So yeah, so we see this handheld copper meter. It's like your cell phone. It's very small. You can take it and use it, and you can get magnetic susceptibility. So this number 17.8 10 to -3 shows you that you have a quite high magnetic susceptibility and you have titanomagnetite in your rock. And here we have a value of 0.3 for these peridotite inclusions in the basalts, showing that we have mainly a paramagnetic mineral in here. So we have seen this figure before because this shows this shows all the sampling sites from our 23 expedition. And I will show you now some magnetic susceptibility measurements, or not yet. No, I will show you so I will show you now some images from the different field sites. So let's start first with the Spitsbergen volcano. We have seen it before. So this is something is. This should be actually an image of Britt's work with the Spitsbergen volcano. Something is missing here, showing the different volcanic units that we have here. So we have the pillow basalts, and we have these platy basalts, and we have these peridotite-bearing basalts, and here again they are very form massive areas, and they stick out. Then they stick out as these less weathered portions, and we have the tuffs also with the bombs of the peridotites, and here also a crossing over these tuff series towards the more massive basalts again. And we have sampled these different these different rock types. And also we have sampled here from Halfdan-Piggen. Yeah, so walked up there, Horst with his big backpack, taking samples from this, from the dike breccia and from the basalts there. And also we have sampled some boulders from the Sigurdfjellet. We haven't climbed up there, but we were successful in finding some of the boulders in the valleys. So that's how we, and I will show you also first preliminary results from this tertiary dike with a contact zone, within the contact zone to the Devonian sandstones. So this is magnetic susceptibility of rocks from the field. And what you can see here is they look all similar, except the ones from Halfdan-Piggen. It's higher compared to Sverrefjellet, for example. And there's also a high magnetic susceptibility in the contact zone of the dike. Yeah, so where we didn't knew in the field, is this just a fine-grained part of the dike? Is it a glassy rim or something, or is it some hornfells from the sediment? So let's have a first look on rock magnetic properties determined now from in the lab. So it's magnetic susceptibility versus natural remanent magnetization. And here it's calculated the Q ratio. It's NRM divided by the induced magnetization, and tells you if a rock is suited for paleomagnetic investigations. Actually, if the value is above 1, as most of the samples are, they are in principle suited for paleomagnetic studies. So this was a test, yeah, and it shows the rocks have high remanences, and the magnetic susceptibilities were known. What we have also done then are some field dependence of magnetic susceptibility. So we have measured magnetic susceptibility in different fields in 330 amps per meter, and compared it to a study here from Vale and Kontny, and there's another one from De Waal, because they found that the field dependence parameter varies with composition of your titanomagnetite. It's a very quick tool to where you can see what is a titanomagnetite in your sample. And as you can see, if we do this for a couple of samples, yeah, so we see we have a large range of compositions that we have seen before we have done any KT curves yet. Scott Keltier, the fine-grained part, yeah, with a very high susceptibility, should be of magnetite, while the others, Scott Keltier samples, have a higher titanium concentration, and Halfdan-Piggen, that is shown here, has also some intermediate composition. So let's have a look if this is true. So Scott Keltier, this is the one, this is the fine-grained rim, and it shows a composition, Curie temperature of 580. It's very close to magnetite, and that fits to what I've shown you before. And we have here some, this is a more coarse-grained inner part, and we see Curie temperatures. Yeah, you see it's very broad. We do not see a Vervi transition actually here. Very broad bumps here with composition, with Curie temperatures between let's say above 400 and between 400 and 500. I think I'm not going into detail into this because that's quite new. It's what's shown here. It's an in-phase and out-of-phase susceptibility. And actually, the out-of-phase temperature dependence of out-of-phase susceptibility, it's not yet so well described, but what we can see there, and that might be quite interesting, is so out-of-phase signal only shows titanomagnetite with an intermediate composition. And maybe the interesting thing is we see an out-of-phase signal here that seems to be hidden here. So there is a titanomagnetite in here in addition to a magnetite. Yeah, so we see we have two different compositions here. And this is also the case in here. So in this broad hump that we are always seeing in our in phase, because that is what people are doing, there can be several compositions hidden in. And that's something has to be further studied. And now Halfdan-piggen, this is the one with a high magnetic susceptibility. And we see, okay, this is a titanomagnetite, very clear, a little bit of irreversibility. So there's something forming. And there is also, as you can see, there is the Curie temperature here is lower than the one here. So there is some irreversibility related to some cation ordering things, and but this is quite normal, I would say, for a alkaline basalt with intermediate compositions. And this is now from the spherofjellet. So this is a platy basalt actually, and here we only see one composition. It's homogeneous titanomagnetite. Yeah. So and the interesting thing here is the Curie temperature is very low. It's extremely low. If you look here, it's below room temperature. Yeah, so Curie temperatures are below room temperatures. It's minus 14. And remember, the magnetic susceptibilities were so low compared to the Halfdan-piggen. And I will show you that this so cannot be if you only look on the magnetic mineralogy in a thin section, because titanomagnetite is very similar in concentration. But let's first have a look on the Scott-Keltier oxide textures. So here, we will hear this later. It's a quite coarse-grained basalt, yeah. So that we see here, and this is also seen in the oxide textures. It's what I've done here. I've coated the polished thin sections by a ferrofluid. And with this, we can see the magnetic phases, titanomagnetites here, more clearly, and we can distinguish them from the ilmenites. So we have here ilmenite and here magnetite, and we see you have these exsolution features. So there seems to be some subaerial oxidation in these, or at least some exsolution features. If you are looking now in the Halfdan-piggen, it's also, I've also coated it, at least here, by this ferrofluid, and all these brown things are the titanomagnetites. Yeah, so a lot of titanomagnetites explains very well the high magnetic susceptibilities, but we also see, chromium spinel, similar to what I've shown you before from the Mythina, surrounded by titanomagnetite. And we see sulfides, we see pyrrhotite and pentlandite as early phases, and they are forming along the fractures in the olivine, yeah, so the mantle olivine. And we also see this hexagonal pyrrhotite transforms during uplift or later events to pyrite and monoclinic pyrrhotite. You see that you have some brownish colors here. This is a transformation from the hexagonal pyrrhotite to the monoclinic. And you have a sequence of the opaque minerals here, from chrome spinel to the sulfides, and then titanomagnetite that has formed from the melt. Okay, and so this is from you, Horst. Actually, you have sent it to me, and here it's a backscattered electron image, and here you also see these titanomagnetite, yeah, and it seems to look like that the decomposition here of this amphibole creates the melt, or is related to some melt formation, and then you have all these titanomagnetites. Now, when we come to spherofjellet, to the oxide textures, it looks very similar to Halfdan-piggen, so it's no difference. Only that we don't have so much sulfide. So we have more sulfides in Halfdan-piggen, and I'm ready. And here, but what is interesting here, the titanomagnetite does not show the ferrofluid, only very little. And it's different in several parts. So here you don't have it. Going a little bit further on, then you see it. And remember, we have this very low Curie temperatures. But what is interesting that there seems to be some different compositions within this rock. Yeah, so so that the glassy parts contain probably different composition, and this is later on maybe interesting to compare it with a rock petrography. Okay, so Spherefjellet and Halfdan-Picken show similar magnetic mineralogy but different magnetic properties. And the reason are the different titanium content in the titanomagnetite creating these different Curie temperatures. And the dike from the Seidfjellet formation is much more coarse-grained and shows titanomagnetite ilmenite assemblage that relates to the composition of the rock actually. Yeah, so more subalkaline and more alkaline compositions. And yeah, the outlook is that we want to do more magnetic data, more magnetic mineralogy data, and that we will do a bachelor's thesis during this year, producing more data and going to publish this work. So thank you very much to the group from the field excursion. It was really a great time. Mm-hmm.
What about any chemical process and appearance, for example, of peptide or peptide that can bring a high susceptibility to Magneto-mineralogy? Did you detect any of these?
So I have seen in vesicles a little bit of goethite and hematite, but goethite and hematite do not produce high magnetic susceptibility, because their susceptibility is not high. High susceptibilities create magnetite, titanomagnetites, but not the goethite.
Any on the measurements or?
Yeah, you would see it actually, but what I have seen up to now is not much weathering. That it's very fresh rocks. Mm-hmm.
Hi, thank you for the nice presentation. My question about Spherefjellet mainly. You showed the platybezel.
Mm-hmm.
So did you sample and did you compare it with the not plated part? Like
Not yet. Not yet.
You're going to do it.
Yes, we are going to do this, but these temperature-dependent measurement, I started with that one because I found it most interesting. Yeah, so and because there we wanted to know is this a weathering effect or what is the effect of this platiness? Okay. But I think it's a very fresh material, and the platiness results to the very rigid behavior of this rock during emplacement and cooling. So I think it's a primary feature, this platiness. Yeah.
This question is perhaps a little off topic, but when I see people use like satellite magnetic measurements to infer the depth, which temperature is gone beyond, and then they infer that like a geotherm from that. They typically assume like a constant Curie temperature, but from your work, it suggests that Curie temperature varies quite a bit.
Yes.
So would you say that these inferences are probably unrealistic?
In part, yes. You have to know where you are. If you have intermediate titanomagnetites with Curie temperatures around room temperature and up to 100 degrees or something, you don't have to assume a Curie term of 3 or 500. It's wrong. Yeah. That's why you have to do such investigations and get a feeling of it. Yeah. Yeah. Good question.